about business. Now we got to switch back to the less weighted values. Lab 6 is up. Char RNN. So this is, remember we talked last time about the unreasonable effectiveness of RNNs. I pointed you to the blog post. For your next lab, you're essentially going to implement this. We've given you a lot of scaffolding code. Hopefully it'll be clear. The essence of the lab is you basically just need to implement a GRU cell and then be able to run it forward and sample from it. So given with the code that we've given you, hopeful this one won't be so bad as some of the previous ones. Speaking of previous, how did style transfer go? Did everybody get it? Working? Eventually?
I was having issues with like my alpha beta ratio to get it to work was like way different than what the paper said. I had like
interesting.
I had like a way higher ratio between them to make it actually do stuff.
Did you divide properly, that normalization, 1 over n squared thing?
Probably not. I don't.
So remember, yeah. So if you're looking for the ratio, the scale probably matters at least a little bit as well. So the normalization may have mattered. Yeah.
I saw this problem in mine and a lot of others where we were able to transfer the brush strokes, but the color didn't transfer like it did in the example.
Did people figure that out? I'm curious.
So for my instance with the alpha beta thing, I could get the ratio to work, but I had to have alpha be less than 1, like 0.01 worked better for me, and then keeping the ratio. And then for color, like if I ran it for 100 or even 1,000 iterations, I get the strokes. If I ran it for 10,000 or 20,000 iterations, I started getting color.
Oh, interesting. I don't remember having to run it that long. Okay, did anybody try SGD as opposed to just Atom? Did that work for you?
It just takes longer.
Okay, I was just curious.
I could have upped the learning rate, but
Okay, it didn't matter.
I used Atom, and then I thought I was doing weird stuff, so I tried to see if it just
Didn't work.
Yeah.
Okay.
Took a long time.
Yeah, so
The one from the paper was terrible.
oh yeah, I'm sorry. I gotta find a better paper. This is like the original paper on the subject, but it is painful, the notation.
Well, no. Atom was way better than the optimizer they used.
Oh, was it?
Yeah.
Okay, good. Yeah, well, that's an old paper, right? I mean,
You should rewrite it.
here's how to get it actually working. Yeah, so I hope it wasn't too painful for you. I really do. I mean, I think hopefully you sense the value in an authentic experience. Right? This is not like getting things to work and learning how to debug it and going through all that, translating a paper that may or may not be excellent into code. Hopefully you sense the value in doing that. I'm sorry it took long, and please let us know how we can tune the labs to better, like I said, we don't want these to be killer. We want them to be useful, but not like epic. It's okay to have an epic lab like once a year, but not every week.
I really liked the paper. I was not a fan of the PyTorch tutorial.
Oh, okay.
Like some of the code was stuff that you replaced with the BGG16, but it was hard to figure out how to redo it, and the way they call stuff and set everything up was really weird, and it was hard to figure out how to like alter the like way we like go through and run things compared to like batch data.
Okay. Yeah. Okay. Good.
On the other side, I love PyTorch tutorials because it gave me a working example that I could say, well, it's supposed to work somehow, and I can check the
Right.
dimensions and stuff, and figure out like it actually is the same dimensions.
Right. Okay. Good. Good to know. Yeah.
Just on the color front, the thing that works for me is making sure that I normalize the image with more pieces into the network every time.
Yeah.
What I'm training towards is the unnormalized image, and then cooking at the end to preserve the color.
Yeah.
You should take
Okay.
that out of the sample code, because that was like huge.
Sorry. Take that.
Yeah, the sample code hasn't normalized the like image when you load it. And so for a long time I was like, oh, I don't need to normalize. But when you normalize after in the forward function, it made a huge difference.
Maybe that's what I was doing.
Yeah. Okay. Good. That's good.
Well, I guess.
Can you send me a note on that? Just like put me up. Okay. Cool. Well, hopefully you at least had fun with it. Did you guys get some cool images? I hope.
Yeah.
Okay, well, we'll keep tuning that lab. Thanks for being good sports about it. Okay, so last time we talked about recurrent DNN, sort of introduction. and we've talked about LSTMs. Today we're going to continue just a little bit our discussion of LSTMs, mostly a review. We pretty much covered them last time, and move on to GRUs as well as applications of recurrent DNNs. Just have a little bit of fun. So I realized, I think I showed you this picture without the legend. Sorry about that. So,
That's much better.
yeah, so here's the LSTM cell. And just as a reminder, inputs are coming in here, so this is like data. C is the thing that we remember, our long-term memory. H is the thing we output at the previous time step, HT minus 1. HT is the thing we're going to output this time step. And CT is the thing we're going to remember at the next time step. And then this HT is the same as this HT. And when we concatenate these things together, we get this sequence of blocks that sort of plug together, and we can use them as part of modeling these recurrent sequences. Okay, so by the way, one thing that was unclear last time, and I apologize, LSTMs are trained in the same way as backprop through time, so they're unrolled over time. And so what that means is when you think about a time series of data, you begin at the beginning and you march through time, several time steps, until you get to the time where you want to output something. And so this is, so let's talk about what that means in terms of a PyTorch implementation. So let's suppose that you already have an LSTM block. And let's suppose you have like a little chunk of code. So what does it mean to unroll something in time in terms of PyTorch? What would that look like? Yeah.
So essentially, whenever you call forward on the net, and you pass in some input, then it's going to perform a series of operations on that input and create a computation graph. And so if you were to call forward on the input and then on the output, continue to call forward on that same variable multiple times in a row, then it's extending this computation graph through time and back covering it through multiple steps.
Yeah, so good. So interestingly enough, unrolling in time, although it might sound complicated, actually is pretty straightforward with PyTorch. So you say something like the following. You say state equals like whatever our initial state is going to be. And this is the H thing. Sorry. This is like H sub 0. And then you'll say something like, for t in range capital T, and you'll say something like,
Will you go back one slide?
oh yeah, so state, comma, output equals, and then you'll say something like forward, and what do you need to sort of pass in?
Input at T. The input at T.
Wait, I'm sorry. So when we call forward, what do you need to pass into this thing to roll to sort of evaluate it? The input, okay, so you have like some sort of data. It will be whatever data you got times t, okay? Then what? Whatever your current state is, and whatever your previous output was. And that will give you a new state and a new output. And then you'll just like somehow emit your output. And then you'll say something like previous state equals state. And then you'll just do it again. So the beauty of PyTorch is that when we think about unrolling for t steps, well, it's literally like just a for loop. So we're just going to say for I equals 1 to t. And we call forward several times. So will this reuse variables properly? Like, will it use the same LSTM variables and W weight matrices and all that stuff? Yeah, absolutely. I mean, as long as you set it up properly, which is actually hard not to do. Yeah.
What does emit output?
Oh, I don't know. This is just like whatever you're going to do with the output. Save it, print it,
Oh, okay, gotcha.
plot it.
Are we calculating one large loss for the unrolled sequence, or are we going to back prop?
Oh, yeah,
In
right.
the
So,
flow
sorry.
as
So there's
well.
also like probably some sort of loss thing, and then you're going to like add some sort of loss function on whatever the output was and whatever the data t plus 1 is, something like that.
And then you just do back prop once.
And then, yeah, and then eventually you'll say something like, do a backwards pass on loss. And maybe you divide by 2. Okay? So that's how we unroll things through time. Yeah, go ahead.
Do the backward pass for every time step t, or after the pass?
No. So we unroll for t time steps and calculate a sequence of losses which we add up or average. And then, so all of this is within for iterations, and blah, blah, blah. And then you'll say something like, take a step. And, okay. Yes.
Okay, so inside the forward function, we have data of t. I'm assuming that's our input vector, right?
Yep.
On this, and
Yep.
then state and
X,
previous
that's-
output is the state
XP. State is
the
CT.
long-term the memory.
Yep. And HT is, remember, it's whatever we output at the last time step. Good?
Good.
Good. Okay, so this is like what you're implementing for your next lab. Ask questions.
So we're talking about the principle of unrolling.
Yes.
It applies to more than just LS.
Absolutely.
But, so a rolled version, just to understand, would be where you would step every time? Or what does it mean to unroll versus?
Yeah, so it's very, very difficult to train a network without unrolling it. So when we unroll it through time, then it's just, we can use regular backprop and like everything works out beautifully. If you want to somehow train the network without unrolling, nobody quite knows how to do that. In the simplest case, you can actually analyze the structure of the network and like come up with a series of simultaneous equations that you then like solve using some crazy like symbolic integrator or something. But like it doesn't hold for the general case and it's not that useful and nobody practice uses it. That's like old school, like way, way, way old school. Back when things were like tractable. Like, I mean, when I say tractable, I mean analytically tractable, i.e. simplistic.
This is like when we talk about like RNNs, unrolled loops is like the examples we're given is kind of in that. Like I thought usually unrolling is like optimization. But yeah.
Yeah, this is kind of like optimization in the sense that we're taking sort of a symbolic declaration of a for loop in some source code, and we're actually like unrolling the loop and sort of seeing each step in it. Under the hood, this is building out a computation graph where each step is represented. So in that sense, it's like compiler optimization with unrolling. Yeah, go ahead.
So the reading, it talks about 3 different types of recurrent networks. One that has recurrent network between hidden connections, and then one that has recurrent connection between the output at one step and the hidden units at the next.
Right.
Is this just one of those specific cases, or which one of the cases is this?
So this is kind of a mix.
Just when you say state, is that like the hidden layer, or is the hidden layer the output?
So all of this I would consider the hidden layer. So you have some input X, it's coming in. You have some complicated hidden layer, which depends on itself, and it's outputting something. And actually, whatever it outputs also feeds back in. So it's a little bit of
in
a
every case, or there's some where there isn't that?
Sorry, in this case.
In this case, okay.
In this case, because the thing that outputs HT gets fed back in at the next time step.
Okay.
And the thing that it generates as far as its hidden state gets fed back in
So it's feeding back both the hidden layer from the previous time step and the output from the current time step.
from the previous time step.
Okay.
Yeah, so it's kind of right in between those, I would say.
So in this drawing, like when you say it feeds back into the H, without like feeding into like H plus 1 kind of a thing, like
Yeah.
we're moving on and it's handing that into the next thing. So like it's still the same H, but like it's the next phase of it. Is that what you're saying? But like through time kind of thing?
Yeah, so in order to calculate the hidden layer activations at xt plus 1, and in order to calculate the output at time t plus 1, you have to know 3 things. You have to know the input, the previous hidden state, and the previous output. Where by hidden state here, it's actually labeled C. It's a little bit funny, but this is, we would call this C.
called H. So basically the unrolling through time is referring to the fact that we're like stepping along like this. Is like
Yes.
Okay.
Yes. Good. Okay. Other questions? All right. Okay, so this is just an example of the of one architecture that you can use that's been very specifically and thoughtfully designed to be able to process time series data. Okay, and remember, we're training them by unrolling through time. So, and just, I thought this was a great image. I found it the other day, and I thought, oh, just so we're like ultimately clear. So the idea is you've got this complicated little octopus here, and it's connected up over time, and these inputs are things like words or characters in sequence-to-sequence architecture where you have something encoding and something decoding. This thing right here has to summarize all of this information, and then that becomes the initial condition for the decoder. And then we just remember that we take whatever it outputs and feed it back in as one of its inputs. By the way, this is a great little read. Deepschool.io has some nice tutorials. Okay, so here's the LSTM architecture in math. So we've seen pictures, but here's what it would look like if we wrote it in a paper, which this is from. So this is from a paper called An Empirical Evaluation of Recurrent Neural Net Architecture. And I'm bringing this up because we're going to study the GRU from this paper, their version of the GRU, and that's the other thing you'll implement for this week's lab. So let's just be clear, their notation is the same as the image that we just saw. So there's an input vector, our hidden layer, and our long-term state. Sorry, I should call that hidden. I should call that previous alpha. Short-term memory, long-term memory. And these are the equations that sort of connect everything together. So if you want to calculate IT here, you call tan H, and then you have two weight matrices, WXI, WHI. And by the way, the subscripting here is meant to connote, this is weight sub xi is the weight matrix that maps x's to i's. So if your dimension of x is, let's say, 1,000, and your dimension of I is, let's say, 100, what shape is WXI going to be?
Or 100.
Annoyingly enough, it is 100 by 1,000, right? So really, if I had named this, I would call this WIX, but I didn't write it. So hopefully that makes sense. So, but this matrix is the matrix with the right shape to take whatever size the x vector is and make it the same size as whatever your I vector is supposed to be. So similarly, the WXF matrix is 1,000 columns by however many rows the F vector has. Okay? So, the last thing is to note we have this thing, what is that? What is it called? It's called the Hadamard product. And it's the element-wise multiplication. So we take two vectors, in this case C1 and FT, and Hadamard multiply them, or element-wise multiply them together. And that gives us our new CT. Okay, so we don't need to go through this in detail. You aren't going to implement this, but you're going to implement the GRU, so we're going to talk about that. So there's a natural question when you look at this LSTM, you're like, well, okay, this seems like crazy. Like, I kind of get it. Like, can we do better? And I thought this paper that I got this from was really a nice paper. So these guys said, they said, yeah, LSTMs, like, they're super popular. Everybody uses them. They empirically seem to work pretty well, but got a lot of pieces, and like, we don't know what's useful and what's not. So they wrote a paper where they did, oh, this is just fantastic. They did a genetic algorithm searching over topologies of little blocks like this. They said they tested over 10,000 of them. And so you can just imagine this server farm, and they have like a pool of like 200 architectures at any time. They train them all, evaluate them against a fitness function, which in this case is generalization performance on current benchmark tasks. And then they take the best ones, they mutate their architectures by adding and removing terms and sort of dynamically creating computation graphs, and then they keep going. And they search the space of possible topologies in this like crazy brute force way. But it's fantastic work, and the conclusions actually were quite interesting. So here's like the table of conclusions. So here's 3 different benchmark time series problems. an arithmetic problem, XML parsing problem, and a Penn tree rank. This is natural language processing. And here's a bunch of architectures. And the numbers here are scores, accuracy, so higher is better. And the things that are bolded were the things that performed best. So in all cases, and so you see over here, there's LSTMs, and they have these subscripts, we'll talk about those in just a second, as well as the GRU, and then these three things. These three things are mutations, so these are just unnamed architectures. So in every case, the unnamed architectures, mutant 1, mutant 2, mutant 3, these were the best performing, okay? But the conclusion of the paper sort of summarized here. So first of all, the GRU outperformed the LSTM on all tasks, with the exception of language modeling. So we see that here. If you compare GRU with LSTM, you should see ever so slightly higher results. Mutant 1 matched GRU's performance, outperformed all other tasks. LSTM significantly outperformed all of the architectures on tree bank when dropout was allowed. And so that's, I forget which one that is. It may not actually be over here. LSTM with a large forget bias outperformed both the LSTM and the GRU on almost all tasks. And while mutant 1 is the best performer of the two music data sets, it's notable that LSTM.I, LSTM-O achieved the best results in the music data set when dropout is used. Music data set was like their held out kind of validation task. And but the real story, kind of the conclusion of the paper was, yeah, like if you're really trying to squeeze every little bit of performance out, and they actually summarize this here, but they said, first of all, the very best performing architecture on any given problem is usually something that's individual and specific to that problem. So it's very rare that you find one thing that works best across all tasks. So if you really, really care, you need to optimize your topology for the task you're working on. But LSTMs actually work pretty well. Like, yes, other things beat them, but actually not by a whole lot. And so I think the line we care about is LSTM-B. So this is the LSTM where you initialize the bias of the forgetting gate in a very specific way. We'll talk about that in just a second. And you can see, like, yeah, it's slightly worse than all these other things, but actually it's pretty good in a lot of different cases. And so I think people have sort of stuck with it. So I think that's the real story here is, actually, surprisingly enough, the LSTM is pretty good, but so is the GRU. And if you initialize the LSTM properly, it works really well. It's a great paper. I encourage you to read it if you care about these kinds of architectures. Okay, so I keep saying GRU. What is that? How does it work? So it's called the gated recurrent unit. Looks a little different than the LSTM, but similar kind of flow. So there's this block. Inputs come in here, X's. It doesn't have a hidden state and an output. It only has an output. And so you have these H's, and then you have a couple of sigmoids and a tanh in the middle, and it's kind of wired in this odd way. This is the picture version. I actually prefer this version, mostly these equations. So this is the thing you're going to implement for your lab. So let's go through and make sure we understand what's going on. So, okay, let's start. So xt comes in and gets farmed out and calculates these three intermediate quantities: zt, rt, and h twiddle t. So let's look at that's twiddle. That's what that's called.
Tilde.
I call it twiddle. It is also a tilde, but in this class it's a twiddle. Okay, so let's look at ht first of all. So ht is the thing that we're going to output. What do you notice about ht and how it's calculated? Who can unpack this in English? Take a look at the equations. Tell me what you notice. Yeah.
Seems to be some interpolation between the h corresponds to the previous hidden state and the h tilde, so whatever, I guess, hidden state with the twiddle.
H twiddle.
The new hidden state that we generate over time.
Okay, right.
And the z is right, this is interpolation time.
Yeah, so I think this is the key, like, to me, this is the key to understanding the GRU. So we're going to calculate some new hidden state / output. And you said it exactly right. This is some interpolation between two things. By the way, why do you say it's an interpolation?
Because you have the z and the 1 -
Yeah, so
It's
anytime,
sigmoided, so it's gonna be.
right, anytime you see a z and a 1 minus z, or foo and 1 minus foo, you should probably think interpolation. Why is that?
That's weird.
Is that how it works? I think it's better, it sounded better.
So the value of z, right, can take between 0 and 1, because we're running through a sigmoid. And so, you know, at one extreme, if z is 0, we're taking one of the terms goes to 0, it disappears, whereas the other one is at 1, it stays the same. On the other side, if z is 1, we keep one of the terms, and then 1 minus 1 is 0, we lose one of the terms. And any value of z in between there is just going to be two different portions of the two things.
Yeah.
One to the other.
Yeah, good. Yeah, I think that's exactly right. Now remember, these are all vectors, and so we're element-wise interpolated. So each element is we're picking sort of either the old one or the new one, or maybe some weighted combination of the two. But the weights will always be positive, and they'll always sum to 1. So that's kind of an important, I don't know, conservation of information thing. It's like you're always, the weights are always positive, and the weights sum to 1. There's a probabilistic interpretation of that as well as an expectation. I see it. Yeah, Curtis?
So would it be reasonable to think of z sub t as like a factor of how important is what just happened compared to the input I'm getting now?
Yes.
How much should I remember?
Yes, exactly. ZT says, how much should I remember? If ZT is high, that means I should just remember what I got and ignore what was just input. If ZT is low, then it's the opposite. I should forget what I remembered and go ahead. So how do you implement this in PyTorch? That's like literally like one line of code. So you take whatever your h variable is, you multiply it with a z, and you can imagine kind of the PyTorch expression for this. So it shouldn't be hard. Okay, and then the rest is kind of just details. So we look here, and so there's this RT thing, which is, and you can sort of see the weight matrices, so it's some combination of the hidden layer and our input and a bias term, and there's a sigmoid, and that gives us R, and then R is used to calculate this H thing, H twiddle, and then there's the Z thing. So Z is the learning what to remember and forget, H is calculating the new thing that we might want to remember, and HT is the final sort of putting it all together.
If you had to give English names to the letters, isn't one called the update date? And the HT is like the candidate new state?
Yeah, that's probably right. So Z is probably the update date. I don't know, is that right?
Yeah, I remember if it's ours and then R is reset.
Yeah, I think R is, what is R? Reset? Reset, and then update, and then candidate, and then output.
So reset is like forgetting?
Yeah, so, I'm not sure, actually, because the way it's used here, I mean, yeah, sort of, because we're taking R and we're pointwise multiplying it against H. So if an R is going to be either 0 or 1 or something in between, so it can definitely be used to selectively eliminate entries in H. So sort of like the forgetting gate. I guess you'd call it the reset gate.
I thought it's the recurrent, like, because it's gated with the recurrent, and the gate is like how much you're allowing to recur or remember.
Yeah, maybe. I actually don't know why they picked these letters. Okay, any other questions on this? Do you feel confident in your ability to implement this? Go ahead.
So one of the papers that I read said that GRUs are better if you have less data because there are fewer parameters, but it trains quicker. Whereas, so it might be better if you have less data, but LSTMs might be better when you have more data and you're able to take more advantage of 3 gates versus 2. Is that true?
Yeah,
Or
I think so. So the jury is out as far as which one you definitively should use. Some people use GRUs, some people use LSTMs. Both are common in practice.
so that generality may or may not hold.
Yeah. As far as I know. Yeah. Okay, any other questions about implementing this? You can do it. Okay, good. Then quickly, just a note, I really liked this discussion in the paper. So they said initialization is important. We've talked about initialization, and we've always said it doesn't matter what you initialize your bias to. Well, here's one example where that's not true. So, important technical detail. Most applications of LSTMs simply initialize the LSTMs with small random weights for torch well-formatting problems. This initialization effectively sets the forget gate to 0.5. The reason for that is if you're initializing with positive or negative numbers, and then it goes through a sigmoid, and sort of the expectation of those numbers is 0, the sigmoid evaluated at 0 gives you 0.5. This introduces a vanishing gradient with a factor of 0.5 per time step. Because if you unroll over time, and you think about the forget gate, which is a multiplication, gradients will be multiplied by 0.5 every time step. And long-term dependencies are particularly severe. This problem is addressed by simply initializing the forget gates BF to a large value, such as 1 or 2. By so doing, the forget gate will be initialized to a value that's close to 1. And what will happen? It's not exactly, so it's funny, but initializing the forget gate to 1 means that you remember things, you pass it through, you're not zeroing things out. And so that means that that path ends up opening up, and it looks like we're multiplying things by something that's close to 1, and so when we back propagate, the gradients don't vanish. It's just like one of those little details about LSTMs. So increase the bias. Yeah, we were talking about this. Okay, so last 10 minutes of class, I just wanted to quickly talk about some applications. So my students pointed me at this fantastic paper called Sketch RNN. That would be kind of fun to go through this in class. So this is a paper that was published about a year ago. And the idea of the paper is let's model hand-drawn sketches of all sorts of stuff. So they have a data set. And the data set looks like these little hand-drawn sketchy things. There's 70,000 examples of this per class, and there's about 100 classes. They use something called bidirectional RNN. We'll see that in just a second. And a slight variation on what we've done using a sequence-to-sequence modeling, and then a temperature thing. And the architecture looks something like this. So, okay, so let's see if we can understand this. So S's are inputs. So the data looks like an XY coordinate of your pen, and then a little 3-bit indicator that says whether your pen was up, whether your pen was down, or whether the drawing should be terminated. So it's just like literally modeling strokes. Okay, so I'm going to give you a time series of X, Y, and then one of the 3-bit indicators, so 5 numbers. I'm going to give you a time series of 5 numbers, and it's going to represent a sketch. And so this is called the forward pass of a recurrent neural net. So you have S's, which are your states, or data. So you have S1, S2, all the way up to Sn. And that just gets fed into your RNN, like normal. But a lot of people have noticed that if you're trying to remember things far in the future, the RNN is problematic because it has to sort of pass information from way back here through all of these hidden states. It's really tough for it to remember things that far back. And so what they do is what's called a bidirectional RNN, where they look at the sequence front to back, but they also look at the sequence back to front. So that's this top pass here, the backward encoder RNN, where they take the data at the end and go backwards through the data all the way back to the beginning. So they do both passes through the data to summarize it, and then it gets summarized, and then they just concatenate the hidden states of both of those together. And then they do a little bit of probabilistic stuff here, and they call the result Z. So Z is the summary of what it's seen so far. And then from there, you want to be able to decode into new segments of the drawing. So sort of like translation, sort of like drawing. And I thought it'd be kind of fun to show you how this works. So they have a little demo online that you can check out. And let me see what's that here. Sketch RNN. All right, cap here, yeah. So there's different models that they've trained it on. You can take your model here. And so we're going to start with palm tree. So it'll load up our palm tree model. And then you can start drawing the palm tree. And it will go ahead and finish drawing it for you. Oh. And it's probabilistic, so it samples different completions of the tree, all of which are consistent with your initial stroke. Okay, so it's learning a time series of drawing. Yeah, like, right? It's got the little bark. I keep watching for it to draw coconuts, but it never has. Yeah, well, maybe I should draw some coconuts. Okay, let's see what I can find. Some coconuts here.
Oh, it's the third one.
Drew an extra one, yeah. Oh, there you go. Nice. Okay. So, so you can, there's all sorts of different versions here of things you can draw. So pig is big. So you can load the pig model. And if I go ahead and, well, it's still loaded. Stand by. Come on. Right. Start drawing pigs. Okay, so there we go. So it's gonna like little body.
Yeah, I think.
So you can have a lot of fun with this. So it's super tribal. This is just it's a ton of fun to play with.
What does it do if you draw like a triangle, like something that's
yeah. So let's see. Good question.
Triangle.
No problem. I can work with that. So yeah, so this is, I thought this is pretty cool. It's a pretty cool example of a time series that is fairly complicated. And, but you get some really interesting results. So I thought it'd be fun to go through just and show you some other results that they have from this. So you can think of this Z vector. So this is the stuff we've drawn, and this is the stuff that has to predict. But you can also think about this kind of in the same way that we've thought about char RNN, where you can sample these things. And that's what it's doing with the image completion. I draw some stuff, it summarizes it into a Z vector, and then samples possible completions, or sample continuations of the time series. But you can think of this Z vector as an encoding of everything that's come up before. And it's just a vector, some 100-dimensional vector. And so what they said is, well, if this is just a vector, can we interpolate in vector space? So let's take the vector. So you draw this vector. I'll go ahead and encode it into a Z. And you draw this thing. I'll go ahead and encode it into a Z. And now I'm going to take those two Z vectors and interpolate between them, and then decode the intermediate sketches. And what you see is a smooth-ish transition between this sketch and this sketch. So it's interpolating, but it's interpolating in sketch space. Of course, it's very different than interpolating directly in pixel space. And the other cool thing that I thought was, they also did this experiment where they said, okay, if Z's are summaries, can we do something called image analogies? So I take this image, and then I add, so this is saying, take the representation for this image, take with body, subtract the head. So like what's left?
The body.
Just the body. So you're taking a cat head, adding a pig body, and you get cat head, pig body. But I mean, yeah, it looks like sort of just a regular thing. Or similarly, take a pig, the head and body. So here we have head minus head and body. So that gives us what? Negative body. So head plus body minus body gives us just head.
Whoa.
Right?
So would you say that it's accurate to say that because this is working in time space and not pixel space, that drawing a head counterclockwise would be different than drawing it clockwise, would be different than drawing it like two different half circles?
Yeah, absolutely.
So like in that previous example, could we assume that you drawing that triangle was it just saying, oh, everybody draws heads first? And
Yeah.
so I'm just gonna draw the bottom.
Yeah, so that's right. So if I started with the tail and then drew the body, yeah, it would be really interesting to see if it could complete it. I don't know that it could. Because it's probably picking up on whatever statistics are in the data set. And the way that people, like the sequence is an important part of that. So absolutely, I think, yeah, so that's probably, yeah, I mean, we could like fiddle around with it and poke at it. But the point is that we're able to model quite complex things with these models. And then, by the way, here's sort of more sketch completions where you give it some sort of preliminary sketch in a class, and it's able to sample different potential completions of your drawing. We'll see more versions of this, by the way, when we get to generative adversarial models. We'll see full image versions of this. Here's the URL for the demo if you want to check it out. It's called SketchRNA. One other thing that I thought would be interesting, just to sort of give you some more ideas about how architectures like this are used in practice. Here's an interesting one, a very similar kind of architecture, but the idea here is that we want to answer questions about images. So I show you an image, and I say something like, what is behind the table? And the idea is that the network has to spit out some words representing the correct answer. So it has to somehow understand what the image has, take the semantic content of your question, combine the two, and then generate an answer using natural language. And so this is like the image captioning thing, except even harder, because now you have to take as input a question as well. And so the architecture is actually pretty straightforward. We use some sort of like pre-trained neural net modeling thing, maybe a VGG, gives us a feature vector. We hand that feature